Welcome, everybody, to the PALS seminar. Today's speaker is Peter Jipsen from Chapman University, and he will speak to us about using Prover 9 for research on ortholattices and locally integral involutive residuated partially ordered monoids. Thank you, Peter.
Thank you. And yeah, thank you very much for having this seminar. It's really been great. I happen to teach at the official time of the seminar this semester, but the fact that these talks are recorded is actually also very valuable. And you know, it pushes up the stress level a little bit. I can't say too much stuff that isn't true, but let's see how it goes. So I gave a talk here in November 2021, which was great. I mean, I really enjoyed that talk. And then what it led to was amazing. It led to a whole research program that's still ongoing, but close to wrapped up, I hope. And it was because of some participants here, and I hope to talk about it someday, but this is not the seminar that I'm going to talk about that particular stuff. This is really about two other projects that are sort of still ongoing. So you're here. So the outline is that the part one is joint work with JB Nation and Ralph Rees at University of Hawaii when I was in sabbatical last spring, which was fantastic, of course. And then part two is joint work with Melissa Sugimoto, which she was an undergraduate here at Chapman when this started. And she's now at CUNY, and she's it continued then with Jose Gilferez and Sid Loria, currently at Chapman. And Sid is also an undergraduate student about to graduate now, but it's about, the first one is on ortholattices and equational basis for a particular variety, and Plonka sums is the second project. So let's see if we can get through this in a reasonable way, because the point of this talk is to actually say something about how tools like Prover 9 Maze 4 can be used fruitfully, and we'll see how successful that is, because ideally I should demonstrate them, but in practice it's easier to just talk about it. And if you want to use them, if you find the ideas in this talk interesting, then it's not hard. That's all you have to know. But there are various options, and sometimes it takes a bit of time or getting some back and forth with somebody who knows how to do stuff, then you get up to speed quickly. So an ortholattice, as you can see here, is just a lattice, but then expanded with a unary operation that satisfies these properties here. So it has to be De Morgan's law obeying operation that is its own inverse, and it's a complement. And so what this means is that also the other De Morgan law will hold automatically, and the operation is order reversing. And that pretty much sums up the simple properties. It's a reasonable expansion of the language of lattice theory that does have some applications, but I'm not that interested in the applications. We were just looking at particular aspects of the theory. And so examples are Boolean algebras, which are really just the distributive ortholattices. And this collection of MONs, they have 2 n elements, and it's n elements paired with the ortholattices. And so with JB and Ralph, we called them M2n, because that's what these things are called in lattice theory. And then there's this one particular ortholattice that is the hexagon, also called the benzene ring. And a typical lattice that's not an ortholattice would be like the pentagon. And the reason it's not an ortholattice is because due to the properties of the ortho complement, there's a pairing between elements and their ortho complement and they cannot be equal because, well, I guess they can be equal if you're in a one element ortholattice, but otherwise they have to be distinct. So the only ortholattice with an odd number of elements has a single element, and otherwise they must have even numbers of elements. So how does all this look inside prover 9, right? Now, prover 9 is an automated theorem prover that existed now for 2 decades. And it's evolved from something that previously was called Otter, and it was created by Bill McCoon. And the latest version is from 2010. And it's still surprisingly useful because it uses a very simple input language. So if you want to use this without installing anything on your computer, you could go to this web page where Google is providing a Python Jupyter notebook in its own, in a flavor of its own. And you would just copy and paste these lines. And the first 3 lines you just copy, paste, and ignore because they can even, ideally you would only need the first line and maybe this part of the 3rd line. But I added a few more things to make stuff a little more straightforward. And then these other lines, they go to a particular GitHub repository, and they download and execute a file that has some added commands in it. So this is prover 9 embedded inside a Python interface, which is easy to use because you don't have to know how to deal with the command line. On the other hand, it's not particularly easy to use because it doesn't have a lot of instructions, but the standard prover 9 Maze 4 manual, which you can find easily online, just search for prover 9, and it'll tell you how to use the syntax and various things, and they're embedded inside Colab or inside Python in a sort of understandable way. And so here's what this means. The OL here is exactly the axioms that you saw on the previous page. The first 2 lines are just the lattice theory axioms, 6 equations, and plus and times are used for join and meet, which is typical in ortholattice theory and in some versions of lattice theory, although wedge and V or V and wedge are more common in textbooks, but it's convenient here. And then this is the part that makes it orthocomplemented, the 3rd line. And then this last line is calling prover 9. And in fact, in the version that I'm using it, this command P9 here, it's calling Maze 4. Maze 4 is something that stands for models and counterexamples. So these are 2 programs, and they do some sensible things. Prover 9 is trying to find a 1st order proof, and Maze 4 is trying to find models of a theory. And right now, just want to show you that if you want to find all the 8 element or up to 8 element models, you would give 2 numbers here. 100 is the time you want to possibly wait. It doesn't take 100 seconds, but the 100 is in seconds. And then 0 is how long you want to prove something. There's nothing to prove because the theory is given here. So the 1st order formulas that you put in are in the 1st argument, and then the things you're trying to prove are as a list in the 2nd argument. And square brackets in Python, square brackets are used for a list of things. And so when you execute this inside Colab, it first installs prover 9. That's what takes 30 seconds. And so the first 3 lines you don't have to repeat. And then after that, you can work with any 1st order theory that you're willing to type in. So it has to be finitely axiomatizable, and it has to be reasonable because these tools cannot do magic. They can do things that would otherwise be tedious by hand. And that's, for example, finding all these models. So this is the output. And here's even a link to the manual if you want a direct link. So it tells us that there's 1 ortholattice with 2 elements. Maze actually doesn't deal with 1 element algebras. It just says they always exist. So I'm not going to tell you about that. But at the end, it lists the fine spectrum, which is a sequence. This is there's one element, one 2 element, and then one 4 element, two 6 element, and 5 8 element models. But what do they look like? And this is where the notebook really makes a difference, because you can ask for, first of all, let's put them all into a single list, because the list L that was produced originally was a list of lists containing all the different sized models independently. And now I want to show them all on one page. So I made a single list of the ones that actually were available as models. And then I'm showing them using the plus operation as the partial order, and then I get this first list. So here are your, I guess it's 9 ortholattices up to size 8. And the pictures aren't perfect. Like here, I would draw it slightly differently, but the computer is just spitting them out. And this doesn't work with the command line version very nicely. And then the second row of pictures is showing the congruence lattices. So here you can see that except for this one and these two, so this second lattice and the last 2 lattices are not subdirectly reducible as ortholattices, but the remaining ones are. And so they generate some varieties of ortholattices that are somehow ordered. And that's one of the things we are investigating here. So OL will be the models of my theory OL. So this is all the ortholattices. And then O standing for 1 element, is the bottom of the lattice of varieties of ortholattices, where everything just coincides. And Prover 9, Maze 4 don't say much about these because they always exist. Boolean algebras is when you add the distributive law. So this is, everything here is modulo the variety OL. And modular ortholattices, you add the modular law, and orthomodular ortholattices, you add this version of the modular law that's slightly weaker. So let's talk about splittings in lattices. For 2 elements in a lattice, the pair AB is a splitting pair if A is not below B, and for every other element of L, either C is above A or C is below B, which really means that we've split the lattice L into a filter above A and an ideal, a principal filter above A and a principal ideal below B. So they're disjoint as an intersection, and together they give all of L. And this helps us understand lattices, and because it kind of separates them into 2 parts, but it doesn't tell you much about how the 2 parts are connected. Right? It's just saying that you can study the 2 parts and at least get some insight. So for example, the 2-element ortholattice, which is the 2-element Boolean algebra, generates a variety of Boolean algebras, and that splits against the 1-element, the variety of all 1-element algebras. And that's because, well, every lattice, here we're still talking about lattices, I guess. In lambda L, every lattice has a 2-element subalgebra, a sublattice precisely if and only if it is non-trivial. But the more interesting splitting that was due to Dedekind early on in lattice theory is that every non-modular lattice has a sublattice isomorphic to N5, the pentagon. But this is also if and only if. So if you're non-modular, you have a pentagon as a sublattice. And if you have a pentagon as a sublattice, then of course you are non-modular. And so that splits and the pictures for this are, well, before you know anything about splittings, you just know that your lattice has a top and a bottom. And it's the complete lattice of all the varieties of let's talk about lattice theory first here. The splitting that I mentioned between D and the one element lattices is this one. So it tells you that you have a single atom. And then the Dedekind splitting against the modular lattices tells you that N5 is sitting over here and everything is divided into this filter and this ideal, and there should be no overlap here. And then there's another splitting, but this last splitting is not a splitting of L. It's a splitting of this part. And that's generally, I think, due to Birkhoff, and it's saying that a modular lattice is non-distributive if and only if it contains this M3. So the interesting thing here is, well, let's say a little bit more. For a complete lattice, splitting varieties can be, well, splitting pairs are actually just a pairing of completely joined prime, or they are equivalent to finding completely joined prime elements in a complete lattice, or completely meet prime elements. And the other part is then determined by, well, if you want to find B, you just take the join of all the things that are not above A. And if you have a splitting pair of varieties, then the first coordinate of the pair is always generated by some countable subdirectly irreducible algebra. And this is because it is really the join of all the varieties generated by its countable members. And since that variety U now is completely joined prime, it means that it has to be equal to one of them. If the theory that you're working in is generated by its finite models, then countable here can be replaced by finite. And on the other side, this variety V, which is called the conjugate variety, is always determined by a single equation. And this equation, or conjugate equation, is the name for it. This is because V is really the intersection of all the varieties that, well, if you look at all the equations that hold in V, and you use each one of them individually, you get a bunch of varieties that contain V. And if you take the intersection of all of them, you get exactly the variety determined by all these equations. But since V is completely meet prime, it has to be equal to one of them. So there's some equation that determines V. And now in orthomodular lattices, there's an interesting splitting which has to do with the orthomodular law and this benzene hexagon. And so let's look at the picture. Here, this is exactly the same picture as for lattice theory that you just saw. But now it's for ortholattices. The difference is that we get Boolean algebras instead of distributive lattices. That's the first splitting. The second splitting, instead of Dedekind's pentagon here, we have the benzene ring. And we even have this third splitting now, which is between Boolean algebras and orthomodular lattices. So inside this ideal, there's a splitting. And it even goes further. There's more results up here about what, there are additional splittings. They have to do with ring theory. And in general, the theory of orthomodular lattices is well studied and somewhat opaque to me because I've concentrated on this side with the project during the sabbatical. So that's what I want to tell you about. Now, generating varieties of ortholattices is straightforward. You just pick your favorite ortholattice A and you construct HSP of it. For example, you can get the MON, the modular ortholattices. They all have height 2 because they come from these M2N lattices. And here's H, the variety generated by the hexagon benzene ring. There's the lambda OL is the complete lattice of all ortholattices, and L plus M will be the horizontal sum of two lattices or two ortholattices. And by that we mean the lattices should be bounded, and we're going to put them next to each other. Well, like there's two lattices. The horizontal sum is just identify the tops and the bottom for the two bounded lattices. For ortholattices, you always have top and bottom bound. And there's a concept of gluing copies of finite Boolean algebras that plays a big role in ortholattice theory, in particular in orthomodular lattices. I'm not going to go into details, but you can look it up. So this is really what the structure looks like. For ortholattices, you have all of them, the orthomodular ones, then the modular ortholattices, that's a proper subvariety. Then you have this chain going up with the odd numbered, the even numbered elements on the MONs. And MO2 even has a list of known covers that are finitely generated. I think the full list is still an open problem. And however, these five, the 1, 2, 3, 4, 5 covers of MO2 come from standard stuff. But the covers of H, they are what I'm going to tell you more about today. And the lattice is known to have 2 to the LF0 many members. And I think for the sub varieties below OML, this is still an open problem, whether there are uncountably many. Obviously, under MO omega, here it's actually known there's just a chain, and so it's countable. Now, there's lots of stuff that isn't known about this lattice, but let's see what we can say. So equational basis for some varieties. In 72, Kirby-Baker proved that if you're in a congruence distributed variety, which is true whenever you have lattice redux, so it's true for lattices and for ortholattices, any finite algebra will generate a variety that has a finite equational basis. And bounded lattices, L and M, we can glue them horizontally. So here I'm making that explicit with the H subscript, but usually I don't write that. When you do this horizontal sum, then orthomodular identity is preserved, in fact. And Brunson-Kalbach proved some things about varieties. Orthomodular lattices that are generated by finite horizontal sums of finite Boolean algebras. They gave equational basis for all those. And in particular, that includes an equational basis for MO2. And you can see it's not worth writing it out in gory detail, but if you use the term CXY, which is sometimes we say that X and Y commute in ortholattices when they have this property that the term is equal to 1. But in order to do MO2, you have to take the join of 3 copies of this term. That's a basis. Now here, let's go back to lattice theory. These are the MNs. They don't have to have an even number of elements because now we're in lattices. Janssen proved that M omega has this particular basis, and MO omega has the same basis. You can use this lattice equational basis for that variety. Mn in lattice theory, this is also from Janssen's paper, it has, we have to be more expressive. You have to be able to talk about something having exactly M atoms. And so, for example, for M3, we have this basis. And M4 has a 5 variable basis. And so if you take the 5 variable basis of M4 and you apply it to ortholattices, you are going to get exactly the variety MO2. And so in fact, we can use this En with an even number, and we get a equational basis for all these varieties that go up on the left-hand side of the picture. But what about H? What about the benzene ring, right? In September 2020, I got an email where John Harding had been contacted by Roberto Gontini, and this is in Sardinia, wanted to know, is there a basis for the variety generated by H? And we thought about it for a while, and I couldn't make any progress on this. It's Kirby's finite basis theorem says that yes, there should be one, but it's not so obvious how to find it. And we had some conjectures. In fact, Roberto already conjectures that this is a basis. And Mackenzie had a basis for N5 in his landmark paper in 1972, and proves that this is a basis of the pentagon. And so that's a natural conjecture that this should be a basis for H. And so when I went on sabbatical January last year, well, I decided that, you know, if I'm in Hawaii and I'm going to talk to JB and Ralph, this is a fun problem. We should try and figure it out. So what do you do? Well, it took a while, but we were sitting in the garden at Jennifer's wonderful apartment there. And we were looking at reducts of ortholattices. So that's RDK. And we were wondering about if you take a map from ortholattices to lattices, where you just forget about the ortho complement, then every variety of ortholattices generates a variety of lattices. And so the question is to describe the range of this map. Will it target H? Will you get H out of as a member in the image of rho? And so that's really the question. When is a variety V of ortholattices determined by an equational basis of the reduct, of the lattice reducts? And first of all, the varieties in the range of rho are not arbitrary lattice varieties, because ortholattices are always self-dual. So if you are coming from a variety of ortholattices, you're only going to get a self-dual variety of lattices. And if K is odd, then VMK is not in the range of rho, for example. Now, the interesting thing about this, that eventually, after a couple of weeks of thinking about it, JB came and said, "Oh, I have an idea. This is what we need to do." And of course, you want to look at subdirect embeddings. And so the theorem that we came up with is that if L is a finite subdirectly reducible lattice, then L is a lattice subdirect factor of an ortholattice if and only if there exists an ortholattice S which has a reduct that subdirectly embeds into L cross L dual. So L itself doesn't have to be self, I mean, L cross L dual will always be something that is self-dual and could potentially have this subdirect embedding into it. And here's the proof for the theorem. You just have to carefully look at how this works. So you take an ortholattice K with a lattice congruence theta that gives you L. And then on K, you can define another congruence by saying that the pairs related by theta prime are exactly the ortho complements related by theta. And then theta prime is another lattice congruence. That's easy to check. And you can say that this factor algebra will be the dual lattice L, and the intersection of theta and theta prime will be an ortho lattice congruence. And this is basically just the observation there. And then you can take the ortho lattice modulo this intersection and call that S. And then the reduct S So S is an ortholattice, but the lattice reduct of S is going to subdirectly embed into these two, which is L cross LD. So that's the interesting direction of this theorem. Now, for example, I mean, for a finite lattice, you can check this. That's the point. And for N5 cross N5 dual, which of course is the same lattice, you can see that when you construct this direct product, there's a copy of the hexagon lattice sitting inside here. And that's what the theorem tells us. So now, if K is an ortholattice with the reduct in the variety generated by N5, then the reduct has a subdirect embedding into a product of copies of N5 and 2, because those are the only subdirectly reducibles in here. And in the proof of the preceding theorem, every N5 congruence is paired with another congruence, theta prime. And so you can look at this theta bar intersection, and we get an embedding of K into the product of these vector algebras and copies of 2. And since this lattice is orthocomplemented and it's the sublattice of N5 cross N5, you can check that we now just have to check that all the subdirect sublattices of N5 cross N5 that admit an orthocomplement are in fact isomorphic to H, so that nothing else can creep into this image of the row funct. And well, this was first checked because it's a finite calculation, but tedious. This was checked by a computer calculation, not with prover 9, right? Just running some little Python script. And then it was later generalized by hand to cover all the lattices, which are the parallel sum of a lattice L and another single element. And parallel sum here means you take a lattice where you add a new, well, you take the union of the two lattices, L and the one element lattice in this case, and then you add a new top and a bottom to make something that looks like that. And then, you know, in general, when you take the parallel sum of L and L dual, this is always going to be orthocomplemented. That's a nice construction. And the theorem is that for any finite subdirectly reducible lattice L, the ortholattice variety generated by this parallel sum is determined by lattice identities. And H is really just the case when L is the two-element lattice, because you take two element lattices and their parallel sum will give you exactly the hexagon. So here is an example of something that is where this is not the case. So there's two different ways. We can take the horizontal sum of two Boolean algebras, where internally these are each Boolean algebras, meaning the complementation stays inside that part. Or we can take this other way of combining two Boolean algebras where the orthocomplement goes across. And they're both ortholattices. And they cannot be distinguished by lattice identities, obviously, but they're not, they do not generate the same variety because the one on the left is orthomodular and the other one has H inside it. For example, here is a copy of H as a sublattice. So now let's look at this picture again. We're now interested, we figured out an equational basis for H, namely Mackenzie's. Ralph Mackenzie's basis for the pentagon is an equational basis for H. But what about the covers of H? In comparison to lattice varieties, a lot is known about the covers of N5. So maybe we should investigate the story for ortholattices. Here, Mackenzie had already found these 15 lattices that generate covers in the 1972 paper. Here is a list of corresponding ortholattices. There's only 9 of them, and we don't know yet if this is the full list of covers, but that's the conjecture. We have some partial results in this direction, and well, it's an interesting problem. So one of the things you can see here, for example, this lattice or this one, they both show you that the variety generated by H will require 3 variables because they generate a covering variety that is given by a lattice that is not 2 generated as an ortholattice, sorry, given by an ortholattice. And where did these pictures come from, right? I mean, in the case of lattice varieties, for this picture, they really just came from Ralph Mackenzie. He played around with lattices enough until he came up with this list, and then it later on turned out it was the complete list. But for here, in this case, we used MACE4 because it can generate models. And we just checked if the models are subdirectly reducible and whether they're the only models that that have the pentagon as a sub-ortholattice, which of course is the case for each of these. And they don't have any other subdirectly irreducibles in the variety that they generate. So it's just themselves. So these are 9 subdirectly irreducible ortholattices that have the the hexagon and the 2-element ortholattice as additional subdirectly irreducible members in their variety. That's something one can check quite easily with the computer, and also, of course, by hand once you know them. Right? And finding them is not necessarily as simple. And one of the interesting things that came out quite a while after we found the equational base, we started thinking about the covers of H. And we knew these 9 once, eventually we knew that there were these 9. But 04 kept popping up in various ways as a crucial member. And it took quite a while for us to realize that, oh, this is actually a splitting ortholattice. And so that gives you some information, because in the splitting diagrams that I showed earlier, from these splittings, you know that Boolean algebras have exactly 2 covers. So finding splitting lattices above H is interesting because it helps you check what's going on with your list of covers. And the theorem, of course, is that in any variety of ortholattices, if O4 is not a member of the variety, then it satisfies a conjugate equation. And this is what the equation looks like. But in practice, you always use this implication because it's slightly simpler. And the result was the fact that it's a splitting equation came out of a Pruva-9 proof with 128 lines. Right? So the interesting thing is that you can write the absence of a finite algebra in a first order way. And that's a formula, that's not an equation. But then if you know an equation, that's another formula. Both of them are first order. So you really just have to prove the equivalence between 2 first order properties. And Pruva-9 was able to do that. And then one had to analyze that proof, which was somewhat interesting. But usually the Pruva-9 proofs are excruciatingly long, and you have to carefully look at what's going on there. And finally, you understand something. When you have a computer, you can find more stuff. So here are additional subdirectly irreducible ortholattices that were found so far. We didn't try to be too complete here, but so the picture currently looks like this. There are 9 over here, which is conjectured to be the full list of finitely generated covers. It's unclear whether there will be infinitely generated covers or not. But, there are other covers that go higher, and one can even say something about the covers of that join, but proving that there aren't any more, and here there are definitely more, that's generally tricky. Here's a summary of the results in the Janssen rival paper that showed that the list of Mackenzie's 15 covers was in fact complete, and that is significant because once you have a complete list of covers, you can easily test if something is a basis for N5. And so Mackenzie's basis is not easy to work with, and neither is any other basis that I've looked at this point. But we can come up with lots of other bases. We just have to find something that fails in all the covers, and at least one of the covers. Sorry, it has to hold in the pentagon, and it must fail in each of the covers. Yeah. And so, since the pentagon's lattice equations also give you an equational basis for H, that's giving us a variety of bases now for H. But if we wanted to test Roberto Guntini's proposed basis, it had ortho complements in it. And so there we would need the full list of covers of H. And so far we just have some partial results. I'm not going to go into details here, but this was an interesting collaboration between lots of ideas and hand calculations, and sometimes checking things with prover 9 just to see if everything still makes sense. But so far it's, well, an interesting conjecture, and the details will be published soon, we hope. I hope. It's up to me here. So now there's some references, and let's look at the second point. This was joint work with Melissa, who's now at CUNY, and Jose Gilfres and Sid Lodia Chapman. And it's about a different type of lattice-ordered algebra. One of my favorite varieties, pointed residuated lattices. These are just residuated lattices with an additional 0 that can be any constant. And such a lattice is called involutive if it satisfies this condition, that the two unary terms that come from using this dualizing element 0 in a specific way, they are called linear negations. The whole thing boils down to classical logic. If you make the simple assumption that the multiplication in the residuated lattice is just the meat, then you get Boolean algebras, and they are the primary example of involutive residuated lattices. And another excellent example are MV algebras. They come from the unit interval with the operations of minimum and maximum for meet and join, and then an operation of circle dot, which is given here. Usually we think of it as the dual operation is truncated addition. It's you add the numbers in the unit interval, and if you go above 1, you just call it 1. And that's the dual operation of this circle. And then you have the identity 1, which if you plug 1 in for x and y, it should give you just the other argument, y, because of this maximum. And there's this linear negation, which is just 1 minus x, which is reflecting the interval around 1/2. So it's called the standard MV algebra, and it has nice connections in geometry. And so, and in logic, of course, it's multi-valued logic. These algebras that show up in the variety generated by, sorry, there's something missing here. There's something not quite right. This is, this V should be outside, and it should be the variety generated by the algebra containing just this one. So that'll have to get fixed before I post these slides. But now, involutive residuated posets are a much more general class of algebras. They're also called IPO monoids, or involutive partially ordered monoids. And they are just the generalizations of involutive residuated lattices, in which the lattice part of the definition up here is replaced with just saying it's a poset, because the rest of the definition doesn't use the lattice operations. So they're just poset ordered. residuated structures. And now we want to know, what can we say about structural results of these things like involutive residuated lattices or residuated po-sets? Well, the point is that finite Boolean algebras at least are very well understood and very important. Classical logic, SAT solving, all kinds of interesting stuff in computer science, and also basically trivial from a mathematical point of view. They're just power set algebras. Even without the finiteness, we consider Boolean algebras reasonably well understood, at least from a universal algebraic point of view, because the variety is generated by the two-element algebra. Then similarly for MV algebras, they are all products of so-called MV chains. And MV chains are just things like this. You have 0, 1/2, 1. So it's a subset of the unit interval that is closed under this negation operation. And of course, it'll be closed under maximum and minimum. And it's also closed under the operation circled up, because 1/2 times 1/2 under that operation turns out to be 0. You're going down in an additive kind of way. And Boolean algebras are idempotent. So, the question that we're trying to address in this project is, can we find larger subclasses of involutive residuated po-sets, maybe even, that are structurally as well understood as these two varieties? And Boolean algebras are idempotent. So this project started in 2018, I think, with 2 visitors that I had from the Sysmix project. This was a precursor of the Mosaic project that's currently ongoing. And they came to California for a month, and we were studying involutive residuated lattices that are idempotent, because idempotency is a huge restriction. And the models looked quite nice. And Maze 4 was able to find all these models up to size 16. And then we noticed that they are constructed in an interesting way. And so in this paper, by the way, we gave a full description of the finite commutative idempotent involutive residuated lattices. And that wasn't simple, but it worked because we had all these pictures and other help from Prover 9. And now we were able to generalize this in a very significant way, I think, because the aim was always idempotence just to get started, but let's see what happens without it. And first, we looked at the partially ordered case. This was work with Melissa, and we were able to prove some partial results, namely that the multiplication of every finite commutative idempotent partially ordered monoid is a Plonka sum of generalized Boolean algebra homomorphisms. But that was just the monoid operation that was obtained in this way. But the construction was already quite generic, and we just weren't able to figure out some particular aspects. But the diagrams that Mace produced for the monoidal order, this is the order that you get from the monoid operation, because you're assuming commutativity and idempotence. You also have associativity because it's a monoid. So this is really a semi-lattice. And these are the pictures of the semi-lattices that show up when you're looking at involutive partially ordered semi-groups. So we're not even assuming an identity element. And there aren't a huge number of models. These are all of them for up to size 6. And so the Boolean components that they are made from, they show up in these pictures with the black lines. Here's what this looks like in Prover 9. Right? Again, you get it to get installed on Colab by these 3 lines, so ignore those, but use them. And then here's the axiomatic theory, and it's just listing out the axioms of IPO monoids with the addition of some idempotence here, and something that helps a little bit if you want to find all the 9-element models. And here I'm showing just the 6-element ones. And that's the list. That's the same picture that previously I made it again with Tixie. This is for the 6-element ones. Actually, this is not the same picture because it's showing the lattice order and the monoidal order. And so it gives you some hints about how you can go back and forth between these, but these are small models. So in general, this is an interesting operation. You're folding the upper Boolean algebra into the lower one, for example, and sometimes they were the same, right? So the general message, because I'm going to run out of time here, is that prover 9 can be helpful when you need to prove that two first order formulas are equivalent. And so you have to be able to put your stuff into first order logic if you want to use that. And the proofs can be annoying, but if it finds a proof, it's great. And it can also check that things are not true, but that's the Mace 4 part. That's turned out to be more interesting from a mathematical research point of view, that it shows you counterexamples. And in particular, it can show you lots of models. And if you can draw these models easily, because looking at operation tables is not a lot of fun, but getting lattice ordered pictures out of it, or semi-lattice ordered pictures, is possible in the notebook interface. And then you can see things that are otherwise not so obvious. Here, the prover, we changed, and we wanted to see what about not assuming idempotence. So let's find weaker axioms instead of commutativity and idempotence. And again, prover 9 was helpful, and we identified these 3 axioms that are now called locally integral. And in residuated lattices, integral just means that the identity is the top element of your algebra. And if you're integral, then you're automatically locally integral. But locally integral is much weaker. And then we were able to prove that there's a nice structure theory for these locally integral IPO monoids. This is a large class, and it includes, without local integrality, just IPO monoids includes all group theory. It includes all partially ordered groups in a very nice way. But if you go to these much better understood Boolean algebras and MV algebras varieties, then you're in fact integral. These are varieties of integral involutive residuated, actually partially ordered monoids, yes. And in fact, they're both lattice ordered, so IL monoids, because the operations turn out to be definable. And so they're actually locally integral. And now here's the current research standing that in general, if you're in any locally integral IPO monoid, and you have a family of homomorphisms that they're just a cone for a functor, then the Plancke sum of this family is going to be the monoidal reduct of A. The negations work just on each component. You can define the partial order. This was the key insight that we were lacking in the previous results with Melissa. And now, when in retrospect, this is quite obvious, and it's really interesting that the partial order on the Plancke sum can be defined from this equation. And therefore, that's the way you recover the partial order on the union of all these components. So Plancke sums in general are a very nice way of constructing complicated stuff. And then there are some other nice consequences that tell you that if the algebra that you started with is nice, then the components are also nice. So this result actually generalizes the result about idempotent commutative involutive residuated lattices, where we could only do it for the finite members, and now it is quite a general structure theory. But the components themselves are more general as well. The components are just integral involutive residuated lattices. And here's an example. Your components are integral, so they each have these local ones. This is the semi-lattice index set over which the Plancke sum is taken. And this is the resulting algebra A that you get. And you can do this gluing, and we worked out the conditions that have to be satisfied for the gluing to succeed. And there's some great pictures here, but I'm afraid I have to just skip some of the details. So there will be more presentations just about this, but the point is some of the aspects of this research would not have been possible without the tool. And so it starts by noticing something, that there's some kind of regularity. The main gluing result here is that if you have some nice axioms on the family of homomorphisms, then you can always construct such a Plonka sum, which we adopted this integral notation for the disjoint union of the components. And here's another example of how you can do this with an infinite chain as a semi-lattice index set, and countably many 4-element algebras patched together. And yeah, there's some open problems here still. One of the conditions wasn't very local when it can be replaced by these three. The question, when is the constructed algebra lattice ordered, is not completely answered yet. And this class of locally integral involutive partially ordered monoids, is it decidable? Or locally integral involutive residuated lattices? Unclear. Involutive residuated lattices in general are decidable, but when you add these three simple axioms, maybe not. Here's some information about equational basis that one can find. So if you're looking inside the lattice of subvarieties of involutive residuated lattices, there are various things you can say here. Again, Boolean algebras show up, just like with ortholattices. Then another family of Sugihara algebras show up. These are these two chains here. And then various others. And here we can actually map out what the lattice looks like, because we have a structure theory. When you have a structure theory, it's pretty easy to draw this lattice and be sure that you have all the covers at some point. In ortholattices and in lattice theory, we don't have a good structure theory. That's, I guess, the message, that we need a better structure theory, and then we can answer these questions, possibly. That's more or less what I wanted to say. Oh, there's something about dual representations, but I think I just need to wrap it up. When you have this representation by Plonka sums, you can try to summarize things even better than the families of homomorphisms in some situations can be replaced by partial functions, because the components can be decomposed into direct products of even simpler pieces. And that's more or less what I wanted to say. So let's leave a few minutes for questions. Thank you.